All right, so we are now at example 2 that brings up the applications, different applications of using how we can apply the central limit theorem. And so let's have a moment reading through our example 2 here. So the beginning description says, mean walking speed is known to be 3.1 miles per hour with standard deviation 1.25 miles per hour. So, and that's all the beginning description is. Question A, for part A sample of 50 people was collected. Find the probability that the mean walking speed of this sample is above 3.47. And so now, connecting the understanding in question A with the beginning description, this is what I need everybody to understand here. So before question A kicks in, the beginning description of the problem introduces us to the population of human being. Really, on Earth here, pretty much anyone is making motion. So we are the humans, even the animals are walking. So let's assume that this study we're doing here in our example 2 is only focused on the human beings. But so we have a really large population of human beings out there, and so everybody is walking. So somebody is walking fast, somebody is walking slower than somebody else. So what I have here is a population of all human beings with different walking speed. And so now immediately the mean walking speed in our population is now known to be 3.1 miles per hour. So right here is one important information. But so realizing that this beginning description of the problem introduces us to the population of human being where any one of us has a walking speed individually. So I would now first introduce a random variable capital X, just a plain capital X, to represent. So my X variable here represents the walking speed, or just simply the walk speed of about one person, or maybe the better wording here is of a person. So any one of us, and like I said earlier, we are now restricting our study to only within the human beings. So immediately, as soon as I define a random variable capital X to represent walking speed of a person right here, then anyone viewing this video can realize that we have a lot of different walking speeds, or in other words, this random variable represents an entire population of human walking speed. And so back on my computer screen here, the beginning description of the problem immediately introduced us to the known mean walking speed. So this mean walking speed is known to be 3.1 miles per hour. Its role here is the population mean. So my point I'm trying to say now is that this population we have here already had a known center, a known population mean. So mu equals 3.1 miles per hour, and allow me to skip the units expression. And further, we know that this population, once we had the center here, average spreading, or formally standard deviation. So clearly speaking, this standard deviation of 1.25 miles per hour, it came attached as part of our beginning description. And so this is clearly a population standard deviation, and being 1.25. And so before I'm moving on too far here, once again, this mean walking speed being 3.1, how I can recognize this mean walking speed to be a population mean simply because it was given, but we did not know out of how many individuals out there. We just simply know that this is given based on some population that had a lot of people. And so likely in the way how it's given without a clear definite sample size indicated, then likely this is its role of this mean value here must be a population mean. And the same argument that goes for this standard deviation. It comes as a partner with this given mean value. So this standard deviation here must also be a population standard deviation. So in other words, we already have a known center, a known population mean, and further we had a known population standard deviation. And so now connecting this beginning description with our question A here, then you see the beginning of question A is saying that a sample of 50 people was collected. So think about if we have any researcher who collect sample of people to measure their walking speed, then this sample, where does this sample come from? This sample is collected from that beginning population. And so that's why I would now refer to this description from the beginning of our problem. I would refer to this population of walking speeds as, this is our beginning population. This term here is just optional, but it enforces the understanding that any sample that we are later going to work with comes out of this beginning population. And so now we are ready for going further into question A. And so in the beginning, as I already highlighted here, a sample of 50 people was collected. Right after we saw this introduction, a sample of 50 people was collected. So now start thinking about this. Once we can pick a sample, once we can collect a sample, anyone can collect a sample, then somebody else can collect the similar sample with the same sample size. So now briefly on scratch work, think about we have a sample size here being 50, and then our sample here is a sample. But if there is a sample, there must be another one. There must be another one. So each sample of size 50 like this will have its own sample mean. So in other words, what I'm trying to say now is that any sample of size 50 that came out from the beginning population will have a sample mean. And so the sample mean of our sample now belongs to a population where I define that as a capital X bar with a subscript 50 here. So my random variable capital X bar subscript 50 represents, this is how about the mean walking speed of a, and how about just gets of a sample of 50 people. So any sample, any group of 50 people has a mean walking speed, and any of those mean walking speed, we refer to those as a sample means, and all of those sample means together is a sampling distribution of the mean, where each sample is at size of 50, and so generally speaking, what we're looking at here is that our sample is one member among the many other sample means, or our sample here our sample mean here in particular is one family is one member in the whole family that we call the sampling distribution of the mean. And so now all of a sudden we realize, once we identify where our beginning population is, picking any sample, then we realize that our sample will have a mean which belongs to a sampling distribution of the mean. So now we have two separate populations of value. And so now the question in our question A, of course, is asking us something that we haven't seen at all throughout our past examples. But so here, as long as we realize that we have a sampling distribution, or in other words, a population of sample means where 50 is the size of each sample, then even though not being asked specifically in the question, but we do need to we do need to ask ourselves these questions. Once we recognize for ourselves a completely brand new population here, a completely brand new distribution, then we must find out what's the value for our center. And we have to also find out what's the average spreading, standard error, or standard deviation on this sampling distribution of the mean. What are the values of these population parameters? So we must know that first, even though the question did not specifically ask for this. So this is where I say we are further applying our central limit theorem understanding right here. Once we already had a known population mean from our beginning population, central limit theorem guarantees that any sampling distribution of the mean must have a center, must have mu x bar equal value with our known mean. So simple enough, we can see mu x bar here will also equal value with 3.1. Even though as I have explained many times that the way we find this, we technically need to find a sample 1, a sample 2, a sample 3, a sample 4, so on and so on. We must find all sample means, then average out just to get this value, which is the same. So why spending so much time? Here we can just quickly see that our final calculated value for mu x bar equals 3.1. Average spreading now on our sampling distribution of the mean here, according to the central limit theorem, it equals our known standard deviation from the beginning population, and we now divide that by the square root of the sample size. Our sample size in this case being 50. Remember, I noted earlier that our sample size here is being 50 people in each sample. In each sample. And remind yourself again that we must know these information before we can answer the actual question being asked in this part A of our example here. So anytime we run into a bottom line here, that anytime we run into a completely brand new sampling distribution of the mean, we must know first thing in line where the center of the data is at, where the center of the population is at, and how much is the average spread on our sampling distribution of the mean values. And then calculation comes out on this sigma x bar of mine is in 4 decimal places here in my example, but when you're doing your actual problem, your online assignments, then make sure you watch for different rounding requirements. So 0.1768. So here I'm going with 4 decimals in my example, in this example. But like I said again, when you're actually starting with your assignments, then make sure you watch for the little instruction about how far to round in each problem when it comes to the sigma x bar value. And so now, after we recognize that we're working with a sampling distribution of the mean where sample size being 50 in each sample, even though it's not specifically asked, but it is now our responsibility to be able to answer these two important questions. Mu x bar, the center of this population, is also at 3.1, the same as our center in the beginning population. Sigma x bar is not exactly 1.25 because in the end we're in a different population compared to our beginning population. Here I purposely wrote down these two populations so anyone can see that we have two different populations. So our sigma x bar here is a much smaller standard deviation compared to our beginning population. And so here is our average spread on this particular sampling distribution of the mean. So the next question, and I'm still not getting anywhere into the actual question in our part A of this example yet. The next, and which is also the third piece of information regarding our sampling distribution of the mean here, is that we want to know whether or not, or I'm starting out with The question, yes or no, is this sampling distribution, is this random variable capital X bar 50 normally distributed? If it would be, then the mean, the center would be at 3.1, and of course standard deviation of this population must be at 0.1768. However, the big question now is that as far as distribution shape, can the distribution shape of this sampling distribution be a nice bell curve and a nice one peak distribution? So the answer is yes or no, and we're about to find out. And so the only answer to this question in order to decide yes or no here, first of all, let's look back at our beginning information. So in our beginning information, we do not know, we only knew the center of our beginning population. Further, we knew the standard deviation of our beginning population. But in the end, as far as distribution shape of our beginning distribution, we had no clue. We didn't know anything regarding the distribution shape. Or in other words, the beginning population is a normal distribution or not. We don't know that. We do not know, we do not have that information whether this beginning population of ours here was a normal distribution. Then so here, in order to answer yes or no here, we must rely on the sample size of our sample. So the answer to this question is now actually yes. But the reason for that now is simply because, so here's my reasoning, because each of our sample size, each of our sample is being 50, which is well above 30. So each of our sample is at size 50, being well above 30. This guarantees that, according to the central limit theorem statement number 2, it guarantees that our sampling distribution here, see, it leads to our sampling distribution capital X bar 50 must be a normal distribution. Okay, so all this result here, so answering yes to this question, but the reasoning that leads to that is simply because we are looking at the sample size being 50 above 30 in each of our sample. So now, as a bottom line, we know that our sampling distribution of the mean, where there are 50 people in each of our sample here, we know that our sampling distribution of the mean is a normal distribution with the center at 3.1 and standard deviation at 0.1768. So upon knowing this information, the next question we want to ask now is, really, what's good about knowing this? Let me remind everybody, this symbolic statement, back in the day we learned about our concept of random variable as well as most particularly the continuous random variable. Then this symbolic statement means we can draw our sampling distribution. We can draw a PDC for our sampling distribution, and the PDC for our sampling distribution in this case now is a bell curve shape. That's what the n mu sigma is all about. So think about, we can place all possible sample mean values where each sample is a group of 50 people, putting all of those values in one horizontal line, low on the left, getting higher to the right hand side. Then we are going to have a PDC being a bell curve like this, where the center right in the middle, this is where the mean value is, 3.1. And of course, so this is mu x bar, and of course sigma x bar, we can never see how sigma can be drawn directly in the picture, but we can always note the sigma value on any bell curve of ours here somewhere next to it. So the sigma value for this particular bell curve is 0.1768 right here. So now, just to re-emphasize what I was saying earlier, we're not only having one sample mean value of the 50 people, we are having infinitely many sample mean values. Some sample mean, some group of 50 people, some sample of 50 people, once we picked it up, we can measure the sample mean, and that sample mean can be above 3.1, staying to the right hand side on this bell curve. Some other sample means of 50 people, when we pick that up, it can turn out to have a mean value below 3.1 right here. And so back to my computer screen, we're now ready to answer our actual question of part A. So the foundation here is that we know we're on a bell curve. This distribution of sample mean size 50 right here is on a bell curve. So find the probability that the mean walking speed of this sample is above 3.47. It's all circulating around this central idea here. We picked a sample of 50 people, but that means once we can pick a sample, then we can also pick another sample. Every sample has a sample mean. And so, say on any particular sample that we picked, what's the chance that the sample there we picked has a sample mean above 3.47? So 3.47 is somewhere to the right hand side on my bell curve right here. And what I need to do now is going to be, I'm going to be looking for that chance. And at this point, everybody is hopefully is fluent enough with how we work on a bell curve right here. So being above 3.47, we are shading the probability above 3.47 is a shaded area to the right hand side of 3.47. And symbolically, this question of ours is simply that question. We want to find P in parentheses. We want any particular sample means that we picked up is to be above 3.47. So this is how we are formulating our symbolic question. And this is graphically how it represents on the bell curve. So the next thing now is to simply find an answer. And so now at this point, once we put ourselves on a bell curve right here, then the usual bell curve work comes back right here. The first thing now is I need to find out 3.7. I need to find out what z-score for 3.7. So 3.47. I am going to subtract the center of the bell curve being 3.1, and then I am going to divide by 0.1768, and then of course this is the z-score for 3.47, and so that z-score there in two decimal places turns out 2.09. And so this part here, we are looking for the z-score of our value 3.47. So in order to have a sample means above 3.47, then any of our sample means need to be above. So think about on the standard z curve, then that would be equivalent to having a z-score above 3.47. I'm just simply giving another reminder of how we operate with any general normal distribution here. But so now obtaining the area to the right hand side of z-score 3.47. This value 3.47 has a z-score 2.09 equivalent on the standard normal distribution. And so now finding the area to the right hand side. What I would do now, I am going to run the LSND program. Or any equivalent technologies. I'm going to go and run LSND program with the provided z-score 2.09. But the idea of this, and I'm sure if you don't like my LSND program, you can use many other technologies, but the idea now is that any technology has an equivalent function to find the area to the left of any z-score, infinitely shaded to the left of any z-score on the bell curve. That's what my LSND is for, once again. But here we're in our problem, our area is shaded to the right hand side. So that area shaded to the left, it needs to be subtracted from 1. So now my final calculation comes out, and this final calculation is where we round to 4 decimal places. My answer comes out in 4 decimal places. 0.0183. So, what is the impact of this, or what is the meaning of this answer? Now, before answering the meaning of this answer right here, allow me to rewrite this final probability answer as a percentage. So this 0.0183 right here is equivalent to 1.83%. What it says here is that once we pick up a sample of 50 people, then that sample of ours will give us a sample mean. But it's not the only sample mean. There are many other sample means, infinitely many other sample means of the same kind. That's why we have an entire bell curve population to represent all of our sample means, capital X bar 50. But now, out of all sample means, or in this particular sample means that we picked up right here, how much chance that our sample mean will come out being above 3.47? So that chance of being above 3.47 is only a 0.0183 chance, or in percentage, it's only 1.83% of time we're going to have a sample mean 50 people with the average above 3.47. And that's what the meaning of this final answer. Now, another thing I would like to clarify before we head out to the next problem is that, you see, so it's starting to get a little dangerous that in these kind of problems we have too many mean values to work with. So a sample of 50 people was collected. Back on my screen here, for example, and find the probability that the mean walking speed. So a lot of time when people see this term mean walking speed, they might be a little confused that, wait a minute, I thought it was already given right here. But the intention of this wording is that this mean walking speed is only the mean walking speed restricted or limited to the sample, or in other words, this mean walking speed here is a sample mean, whereas the mean walking speed given before this question of part A is a population mean. So this population means, good thing we already knew it. Once we knew it, this population mean walking speed here is independent with any sample. Maybe we pick a sample, now we have a 3.15, maybe we pick another sample there, that walking speed there, that sample walking speed there is a 3.4, maybe we pick a third sample, that walking speed on the third sample is a 2.99. But so what I'm trying to say now is that the mean walking speed here is the sample mean that comes out from this sample as described here, and its difference with this mean walking speed here is known to be a population walking speed, population mean walking speed, where somebody already did the hard work and went through the entire population to come up with this population mean value for us. So these two mean values are completely different. And now we are at question B, or part B of our example that we're currently working with. This is example 2, part B. So now in part B, we're starting out with a sample of 100 people was collected. Find the probability that the sample mean is above 3.47. So reading through this question word by word right here, a sample of 100 people was collected. This now indicates for us that we are no longer working with capital X bar 50 as in the earlier part, but we are now working with capital X bar 100. The idea now is that, once again, we can pick a sample. Once we can pick a sample of 100 people, we can pick another sample of the same sample size, and we can pick another sample of the same sample size. Any of our samples of 100 people can give us a sample mean. And so all of those sample means of size 100 each is generally regarded as a random variable capital X bar 100. So this capital X bar 100 represents the mean walking speed of a sample. But this time, instead of 50, we're looking at 100 people. So we changed to a different sample size. And so now, after being through with part A of this example, then we can start speeding up the process here a little bit, but very similar responsibility here. First, we need to know that we are already in a completely brand new population of sample means. Once again, we pick these samples to get sample means from our same beginning population here. So from the population of individual walking speed on each person, then we already had a known mean value, a known center of that population. We further had a known standard deviation of that population. So here, back into this sampling distribution of the sample means, then we need to recognize, even though the question on this computer screen did not ask us any of this question specifically, but it is our responsibility to find. We need to find out what is our value of the mu x bar. So quickly, according to the central limit theorem, mu x bar here must be 3.1. The next question after center, so this is center. And now you can see that as I'm speeding up the process here, the reason I can speed up the process here is because we have seen these actions in the earlier example quite step by step. And so after center being referred to as the mu x bar, then average spread is the sigma x bar standard deviation of all sample means. This average spread now is from our known standard deviation 1.25, we are going to divide by the sample size. Now the sample size in each of our sample in this case here as a reminder. So n here equals 100. We're indicating that we're looking at in each sample. So there are 100 people in each sample. And so here I'm going to divide by square root of 100. Calculation comes out to be 0.125. And so now I refer to all this. The meaning of all of sigma x bar is the average spreading, or for short, the average spread of all sample mean values from the center. So knowing center, now we know center, now we know average spread. The next step once again is to decide, because at this point anyone viewing this video is well aware that we are going to have infinitely many sample means value where each sample is 100 people. And so having such a large population of sample means of size 100, we want to know if this capital X bar as a population of sample means can be normally distributed at center 3.1 and standard deviation 0.125 or not. So the big concern here is, we're looking now at this distribution shape. Is this going to be a bell curve distribution or not? And so the answer waiting for us could be a yes or it could be a no. And now once again I am going to answer for everybody that the answer here must be yes. The reason for this, once again, let's look back at our beginning population. Once again, we only knew the population mean value here. Further, we knew the population standard deviation, but that was all we knew. We did not know whether our population in the beginning was a bell curve or not. And so in order to say yes that this sampling distribution of the mean would form into a bell curve or would be normally distributed, we use the reasoning where, so the reason lead to that is because So I had a yes here simply because our sample size that we are using being 100. We're having a sample size which is much above 30. And then as a quick explanation, as long as we have a sample size being way above 30 like that, then it guarantees no matter if our beginning population being a bell curve or not, but it will automatically guarantee that our sampling distribution of the mean will be normally distributed. 3.1 with 0.125 as a standard deviation. All right, so now knowing that our sampling distribution capital X bar 100 is normally distributed with the center at 3.1 and the population standard deviation and the average spread at 0.125. We can now draw this graphically on a bell curve. You can now draw a bell curve. And once again, on this bell curve, think about this horizontal line from low to high is where all values, different sample mean values of capital X bar 100 are being arranged. And once again, the center, similar to part A, the center of this bell curve is at 3.1 as found here. So this is mu X bar. And our sampling distribution here has this bell curve, this PDC has a sigma value, and here symbolically sigma X bar being value at 0.125. And so now we are, and so this once again reinforces the fact that there are infinitely many values of sample means where each sample is 100 people. Some sample means of 100 people are below 3.1. Some other sample means in this kind is above 3.1. So let's say in any sample that we picked, how much chance, and back to my computer screen right here, this is what the question is asking. Find the probability that the sample mean of any sample mean of this kind right here, the sample mean is above 3.47. So symbolically, this is P in parentheses, capital X bar 100. We're looking for it to be above 3.47. And that means from low to high, and center is right in the middle, among all infinitely many sample means here, 3.47 is about out here somewhere to the right hand side of the center. This probability is a shaded area, shaded to the right hand side again. And so now it's a completely brand new bell curve problem for us here. So relatively to this bell curve, this PDC here, be 3.47 on our bell curve. Let's subtract the center, 3.1, and divide by 0.125, the standard deviation on this current bell curve. What we're looking at here is the z-score for 3.47. Calculation comes out to be 2.96. So that means on this particular limit right here, at this particular limit, the equivalent z-score on the standard normal distribution is a 2.96. That means looking for a sample means being above 3.47 is the same as on the standard normal distribution curve. We're looking for the z-score being above 2.96. And so once again, the way of finding this, once we had a z-score in 2 decimals, I am going to provide that into my LSND. So running the LSND program or some equivalent technology out there over the web to find the area to the left of 2.96. So if anyone at this point in the quarter still struggle using my LSND program, the idea now is that this is just to find some area shaded to the left-hand side of the given z-score on the standard normal distribution. So you don't have to stick with my LS&D program. You can find tons of other resources over the web that allows you to do this. After we found the area to the left of 2.96, then which is equivalent to this area to the left here, but our answer as an area is being shaded to the right-hand side. So to find the actual final answer, we're going to need to subtract our answer from the LS&D program from 1. And so now final calculation comes out to be the area to the left of z-score 2.96, or the area to the left of this 3.47 on this bell curve is a 0.9984618. But then, as a reminder, we're subtracting this from 1. And so our final answer here in 4 decimal places, decimal comes out to be 0.0014. So any of these calculations, try to get as many decimals as we can. Normally I would go with about 6 to 7 or 8 decimals here. But the very final answer, then we round to 4 decimal place on standard. And so here this is a 0.0014 chance to have a sample mean in a sample of 100 people being above 3.47. And that chance here in percentage, it's equivalent to a 0.14%. So once again, allow me to explain the meaning of that again. But out of infinitely many sample means where each sample is 100, then out of infinitely many of those sample means, the chance of finding a sample mean being above 3.47 in this way is only a 0.14% of chance, or 0.0014 probability.